Welcome to Fundamentals of Artificial Intelligence. We continue our discussion on knowledge representation and reasoning. In the last lecture, we have looked at resolution in first order logic and have walked through resolution refutation proofs. Proof within a logical inference system can be applied for information retrieval or automatic problem solving. These applications have procedures to extract the information from the proof once they are found. One such procedure is the procedure of answer extraction, which extracts the information about an existentially quantified variable in the goal from proofs using the resolution principle. This is what we will look in more depth today in our lecture. So here is our Block's world problem that we have introduced in the last lecture. There are three colored blocks stacked as shown. The top one is green and the bottom one is not green. Now the query is there a green block on top of a non-green block? Now can a first order logic inference system answer such a query? So if you look at the query, we can write it as there exists x, there exists y on x comma y and green x and not green y, where the predicate on holds if and only if a block x is immediately above another block y. A predicate green x is to mean that the block is green, and a predicate negation of green of x would mean that the block is non-green. Now given these predicates and the scenario that is being shown here, where I have a green block at the top, a block B which whether it is green or not green is not known, and a block C which is non-green, is there a process to confirm that there is a green block on top of a non-green block? Now intuitively, if you argue in this system, you could see that B could be either green or not green. If B is a green block, then this statement is true, because I have a green block which is B on top of a non-green block which is C. On the other hand, if B is a non-green block, then also the statement is true, because then I have A which is a green block on top of B which is a non-green block. Now in order to show that this statement is true, what we do in a resolution refutation proof is we take the negation of the query. So we write here not there exists x, there exists y on x comma y and green x and not green y. And if you push the negation symbol inside, we will have for all x for all y not of this, and then I can get to the clause form. So this statement here is the clausal normal form of the negation of the query, and what I have on the right of your screen is the refutation trace to finally arrive at the empty clause. So the statement that there is a green block on a non-green block is logically implied by the set of clauses that I get from the initial scenario. But one thing to note here is the following, that in this problem the knowledge base entails that there is some block which must be green on top of a non-green block. However, what it does not do is it does not make any commitment to any specific one. So, it does not tell us whether this statement is true because the block B is green, or the statement is true because block B is non-green. We have no answer to what the existentially quantified variables are. So, answer extraction deals with providing instances for such variables. Now, extracting answers from refutation proofs, there are many applications of first order logic theorem proving systems which look at this. Proving formulas that contain existentially quantified variables and finding values or instances of these variables would mean that I could not only talk of that there is a x such that W of x logically follows from the initial clause set, I would also be able to get an instance of the x. Doing this, I can produce the satisfying instance for x. Now, this requires that the proof method is constructive. Let us take 1 minute to understand what is a constructive proof. A constructive proof is a proof that directly provides a specific example or which gives an algorithm for producing an example. So, in a sense, constructive proofs are called demonstrative proofs because they demonstrate the existence of the existentially quantified variable by showing us an example of that particular object. There is a huge consequence of the prospect of producing satisfying instances for existentially quantified variables. This allows the possibility for posing quite general questions. Like for example, I could ask a question like, does there exist a solution sequence to a certain 8 puzzle? Now, if I ask that question and I have a demonstrative proof that there exists a solution sequence to a certain 8 puzzle, that would mean that I also have the path to the solution. So, if a constructive proof could be found that a solution does exist, this could mean that we can produce the desired solution as well. Or it could even be stressed further to, I could ask whether there exist programs that perform desired computation. Now, if I can have a constructive proof of a program's existence, then one could produce the desired program. One needs to understand though that complex questions will in the first place require very complex proofs, possibly so complex that our automatic procedures that we have in place would not find a proof in the first place. So, making these ideas not feasible in practice. However, it is interesting to note that if I can extract answers from refutation proofs, that is, I can produce satisfying instances for existentially quantified variables, then it allows the possibility for posing quite general questions and have wide implications. Let us take a simple example first and try to understand the answer extraction process. Here we will talk of resolution, refutation being performed, and then how that refutation tree is converted to a modified proof tree to get to the answer, but this discussion will be a little casual and then we will look at more depth on how this is done after we have done with this example. So, here is a very popular nursery rhyme. Mary had a little lamb, its fleece was white as snow, and everywhere that Mary went, the lamb was sure to go. This, if you hear, then you know that the lamb goes wherever Mary goes, and then at one point of time I am told that Mary is at school. So, if I ask you where is the lamb, one can very well answer that the lamb is at the school. How do you find such an answer within a first order logic resolution system? So, here if you see, the problem specifies two facts. One, that the lamb goes wherever Mary goes. Two, that Mary is at school. And from these facts, the answer can presumably be deduced. In order to do that, I must first convert the facts into the clause set, and then I should be able to prove the existence of a place where the lamp is. So, the question, where is the lamp? To answer this question, we first prove that there is some place where the lamp is. So, we say there is an x at lamp comma x. Now, just to take a note here, that the predicate being used here is at x comma y to mean that x is at place y. So, here the statement lamb goes wherever Mary goes, instead of bothering about places and other things, I have introduced a predicate at to say that for all x, if Mary is at x, the lamp will also be at x. So, this is the final result of that particular statement. Now, the next statement says Mary is at school. So, I have a statement here at Mary comma school. Where is the lamb? I would have to have an existential that there is an x at lamb comma x. I take the negation of this statement and then try to get a resolution refutation done. But before that, let us see the key idea. The key idea is to convert the question to a goal well formed formula which contains an existential quantifier. Now, the existentially quantified variable actually represents an answer to the question. If the question can be answered from the clause set, that is the facts given, then the goal well formed formula created in this manner will logically follow from the clausal set. So, after obtaining the proof, we try to extract an instance of the existentially quantified variable to serve as an answer. So, coming back to the example, we had this existentially quantified statement, there exists x at lamb comma x. We take the negation of the goal statement and also we convert the two facts given to us. So, the implication is left out and I have this already in a clausal normal form. So, I have these three clauses. Here is the resolution trace of this problem. So, the resolution refutation is obtained in the usual manner. The figure on the left is the refutation tree. So, here is the negation of the goal not at lamb comma x, and here is the statement saying the lamb goes wherever Mary goes. From that I have not at Mary comma x, and then I know Mary is at the school. So, using a substitution which is school for x, I have the empty clause. This was about getting to the proof of the statement that there is some place where the lamp is. But then the idea is to get to the particular place, that is, what is the value of that existentially quantified variable x in the goal well-formed formula. So, the process for extracting the answer for the question, where is the lamb, is as follows. I append each clause arising from the negation of the goal to its negation. That is, this was the statement which was negation of the goal. If I append this to its own negation, that means I would be converting a tautology. So, basically this statement here, the goal well-formed formula, is converted to a tautology, and then you follow the structure of the refutation tree. So, when I mean follow the structure of the refutation tree, I mean that you perform the same resolutions and use the same unifications there. Finally, the clause that you have at the root will be the answer that we are looking for. So, the figure on your right now shows the modified proof tree, where the negation of the goal together with its own negation has been added up, and we have a tautology, and we follow the same resolutions of the refutation tree. So, first we resolve it wherever Mary goes, the lamb goes, and we use the same unification, and here instead of at Mary x, I have not at Mary x or at lamb comma x, and then this substitution school for x, instead of an empty clause at the root, now I have at lamb comma school. This is interesting to note that the answer statement that I have got here is of the same form to that of the goal. Only difference is that now I have a constant here, school, in place of the existentially quantified variable in the goal, and this is the answer to the question, where is the lamb. So, I could say the lamb is at the school. So, let us now look at in more depth the process of answer extraction and try to understand why it works. Answer extraction involves converting a refutation tree to a proof tree with statement at the root that can be used as an answer. You convert every clause arising from the negation of the goal well-formed formula into a tautology. So, the statement at the root of the modified proof tree logically follows from the axioms and from the tautologies, and hence we could say that it follows from the axioms alone. So, the modified proof tree, by the very fact that it works on tautologies and the axioms, justifies answer extraction. So, answer extraction can also be looked at as answering a fill in the blank question. Like, I could think of a fill in the blank question as a predicate calculus sentence with free variables which specify the blanks to be filled in. So, the goal is to find bindings for the free variables such that when the database logically implies the sentence obtained by substituting the bindings into the original question, the gap has been filled up and I know what is the answer to my question. So, answer literal for a fill in the blank question phi is a term of the form answer v1 to vn, where v1 to vn are the free variables in phi. Now, to answer phi, we form a disjunction. Of course, we take the negation of the question being asked. So, we take negation of phi and we take the answer literals and convert it to a clausal form. Let us take an example to understand how this happens and how I arrive at the answer. So, consider the following sentences. Aryan is the father of Jivan. Bhuban is the father of Kavya. Fathers are parents. So, if I ask you now who is Jivan's parent, then you know fathers are parents and you know Aryan is father of Jivan. So, the answer could be that Aryan is the parent of Jivan. In order to ask this question, I will first say there exists an X who is a parent of Jivan, and then I could think of writing the facts of the problem given to me. The first is father Aryan comma Jivan, the next is father Bhuban comma Kavya, and then a rule which is saying that for all x for all y, x is the father of y means x is the parent of y. Now, in order to do a fill in the blank question answering, I can take the negation of the goal, which is not of there exists parent x comma Jivan, and this is not parent x comma Jivan. I could add the answer literal, answer of x, and thereafter I could do a resolution proof for this. So, here is the resolution trace where I have added gamma, which is not only negation of the goal statement, but also an answer literal, and I could resolve between 1 and 3 to have parent Aryan comma Jivan. I could resolve 2 and 3 to have parent Bhuban comma Kavya, and then I could do a resolution between 3 and 4 to have not father x comma Jivan and the answer literal as answer x. Now, the resolution between these two here one needs to look at again. See, here I have x for z and Jivan for y, and that leads to not father x comma Jivan, answer x. Now, we could see that when I resolve 4 and 5, I have answer as Aryan, or I resolve 1 and 7, I have answer as Aryan. Rather than the empty clause, as would have come out if this was a resolution proof, the procedure here halts as soon as it derives a clause consisting of only the answer literals. And this procedure produces only one answer literal. If it does that, the term it contains constitute the only answer to the question. But this is not always the case. Suppose the database had both the father and the mother of Jivan, and we ask the same question, who is the parent of Jivan? In such a case, the resolution trace, if we see here, can derive two answers to this question. One, if I have a fact that Annie is the mother of Jivan, and another that Aryan is the father of Jivan, I could have an answer that says Aryan, and I could equally have an answer that says Annie. Of course, I have to have rules here saying every mother is a parent, every father is a parent, and I am looking for the answer to a question which is who is the parent of Jivan, therefore, I have added a answer literal. Now, the resolution trace shows that we can derive two answers to this question. However, we have no way of knowing whether or not the answer statement from the given refutation exhausts all possibilities. Are there more answers? There is no way of knowing whether there are more answers or not. Now, instead of that, if I have cases that have disjunctions in the database, I can yield a clause containing more than one answer literal. Significance of this is that no answer is guaranteed to work, but then one of the answers must be correct. So, let us try to understand this with an example. Here is an example where I have a disjunction in the database. So, the database here has a statement saying Aryan is the father of Jivan or Bhavesh is the father of Jivan. Now, if I was looking for an answer who is Jivan's father, I would have added the negation of the goal, which is not father Z comma Jivan, and as I was doing fill in the blank, I would have added an answer literal saying answer Z. Now, given such a scenario where I have a disjunction, I can always get a second clause. Like, let us say what we mean by a second clause after arriving at an answer. Like, if you resolve 1 and 2, then you could see that here Aryan would be for Z and these would go away, that is the complementary pair. I would be left with father Bhavesh comma Jivan and my answer literal. I know Aryan has been substituted for Z, so I have an answer which says Aryan. So, this is my first answer which says who is the father of Jivan, and that is Aryan. But now, if you look at clause 3 and clause 2, you could see that you could resolve these clauses. Here is my complementary pair, this one and this one, father Bhavesh comma Jivan, not father Z comma Jivan. So, Bhavesh for Z, I can resolve this and then I would have an answer which would be Aryan or Bhavesh. And this is something that one needs to understand, that some cases the answer extraction procedure can yield a clause containing more than one answer literal. And in such a case, no one single answer is guaranteed to work, but then we need to realize that one of the answers must be correct. This is precisely because we get a clause second time after arriving at the answer. We can continue searching in hope of finding a more specific answer. However, given the undecidability of logical implication, we can never know in general whether we have exhausted all possibilities, whether we can stop and say no more specific answers exist. This is something that eludes us in answer extraction. So, the answer extraction process that we have discussed today, to summarize, the steps of the answer extraction process are the following. 1. First, the resolution refutation tree is found. So, here the most important fact to be marked is the unification subsets of the clauses, because when I am trying to get the modified proof tree, I have to go through the same resolutions That is, I use the same unification subsets of the clauses. Next, if I have Skolem functions, new variables are substituted in the clauses from the negation of the goal, and clauses resulting from negation of the goal are converted into tautologies. Modified proof tree is produced, replicating the structure of the original refutation tree. So, the structure must remain the same and use a unification set which is determined by the original unification set, and therefore, we have to mark the unification set of the clauses while we are doing the resolution refutation. Clauses at the root of the modified tree is the answer to the question that we are looking at. The final statement of the modified proof tree, that is the answer statement, depends upon the refutation which is replicated. Now, one needs to remember that several different refutations may exist for the same problem, and from each an answer statement could be extracted. Some of these answers that I have extracted may be identical, some more general than the others, but then as I had emphasized, we do not know if we could get a more general answer, and we do not know when to stop looking for more general or more specific answers. This is because of the very fact that predicate calculus is undecidable. So, the undecidability of predicate calculus would mean that we would not always know whether we have found all possible proofs, but one could of course continue to search for proofs until one has found one producing a sufficiently general answer. So, this is what we have covered in answer extraction. In our next lecture, we will look at certain strategies that we use while we are working through resolution refutation proof systems. Thank you very much.